Okay, after our problem session yesterday, the Friday the 12th, what I want to do is just give you a couple things on the problems that I saw people having the most. So if you didn't have any problems, then you can stop. If you did, then here's what I saw the common mistakes were. Number one, when we're talking about polar versus non-polar. When you first of all have to draw the Lewis dot structure and then convert it to a three-dimensional structure using Vesper theory. But when you have your geometry, whether it's linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral, the molecule will be non-polar if all of the positions have the same atom bonded to it. If they don't have the same atom bonded to it, or if there's a lone pair at one of those positions, then the molecule will most likely be polar as long as the bond dipoles don't cancel each other out. So one of the problems that you had yesterday was the PF5. So PF5 would have this trigonal bipyramidal geometry. As long as all the positions are filled by fluorines, then this would be nonpolar. If, however, one of the positions had a lone pair on it or another atom, then what you would have is then, as long as the bond dipoles don't cancel each other out, it would be polar. Another one was the CS2. So we had a sulfur double bonded to the carbon, and then there was an S on this side. That's linear, so the two bond dipoles cancel. The SO2, however, would have looked, this is one of the resonance structures that you could have drawn. And in this case, it's trigonal bipyramidal, or trigonal planar, sorry. But with the lone pairs, we don't ever draw arrows to the lone pairs. We only draw arrows to the atoms. So in this case, the lone pair causes the geometry to be, well, molecular geometry to be bent. And so therefore SO2 is not linear, and therefore it is polar, while the CS2 is nonpolar. So again, when you're looking at polarity, you never draw arrows to the electrons, but the electrons do come into play in terms of drawing the Lewis dot structure, and then you always have to convert it to the Vesper theory, using Vesper to the three-dimensional geometry. Okay, so you want to make sure that, when you draw the molecule out, that you're looking for symmetry, and if it's perfectly symmetrical, then it will not be polar. But if there's anything that breaks up the symmetry, like another atom or a lone pair, then it will become polar. So that was one thing. Then the other issue that people have was about the polar and nonpolar molecules filtering into intermolecular forces. So basically your steps for determining your polar and your intermolecular forces are the molecules polar or are they nonpolar? And if they're both nonpolar, then you're going to have dispersion forces. If they're both polar, then you could either have hydrogen bonding, or you could have dipole-dipole. It's going to depend on whether or not there is a hydrogen bond present. So that's your first step. Polar versus nonpolar. Nonpolar, easy, it's dispersion. For polar molecules, you need to look at hydrogen bonding, which brings up the question of what is a hydrogen bond. So remember that a hydrogen bond, the hydrogen is going to be covalently attached to one atom, and then the hydrogen bond forms to another atom. And those atoms, the atom that it's covalently bonded to and the atom that it's hydrogen bonded to, so in other words, I'll just write this is a covalent bond and this is the so-called hydrogen bond. Those atoms can either be oxygen, nitrogen, or fluorine. And so for you to have a hydrogen bond, the hydrogen has to be covalently bonded to oxygen, nitrogen, or fluorine, and then hydrogen bonded to oxygen, nitrogen, or fluorine. And so that's what would then give you the hydrogen bond, which would give you hydrogen bonding as your strongest intermolecular force. So for instance, if you had something like a CH3SH and water, and I said, what's the strongest intermolecular force between them? Well, in this case, the only thing that could happen is, well, there's two things that could happen. You could have the hydrogen attached to the sulfur be attracted to the oxygen, which it actually would be, because the sulfur is slightly negative, the hydrogen is slightly positive, and the oxygen on the other side is slightly negative. Just in terms of its, bond, just in terms of its polar covalent bonds. Is this a hydrogen bond, though? No, it's not a hydrogen bond, because the hydrogen may be bonded to oxygen through this electrostatic attraction, but the covalent bond is to sulfur, which is not one of the three. And the same thing would be true if I decided to say, okay, well, let's take one of the hydrogens on the oxygen. I could then say, is this a hydrogen bond? And the answer is, no, that's not a hydrogen bond either, because the hydrogen would have to be hydrogen bonded to sulfur, but sulfur is not one of the three elements. It's not oxygen, nitrogen, or fluorine. Now, what could be a hydrogen bond? Let's say you had a CH3 attached to an oxygen attached to another CH3, and you had a water molecule. In this case, that can be a hydrogen bond, because now the hydrogen is attracted to the oxygen, covalently bonded to an oxygen. So yes, that would be a hydrogen bond. Someone else asked along the way, they said, does an atom that's going to form a hydrogen bond have to have lone pairs? Yes, because how is, in essence, this hydrogen being attracted to that oxygen? It's, in essence, being attracted to it by that lone pair. But when we really talk about this, we're talking about electrostatic attractions between oxygens and hydrogen. And so whether you look at it as the hydrogen being bonded with the lone pair, which would give hydrogen two bonds, which it's really not allowed to have, it's more of an electrostatic attraction. But in general, for the hydrogen to form a hydrogen bond, it has to have a lone pair. But then again, the oxygen, the nitrogen, and the fluorine all have a lone pair that they could use to bond that hydrogen. So those were the biggest issues that I saw people have. So again, if you had problems with that, hopefully this clears it up. If not, if you were fine, then you didn't make it to the end of the tape.